When we look at the next stage of glucose degradation, well, what we're doing is, again, converting all the molecules into different pools of energy. And so the energy molecule that we have was all the carbons in glucose that could be oxidized. Okay? We've taken those electrons and reduced electron carriers. So we have a bunch of NADHs that were created, and we created in both places, glycolysis and citric acid cycle. We also created the energy molecule ATP, some of them in the cytosol already, which is ultimately where they're going to be and be used. And we've, at different stages, have created molecules, but we eventually, through the citric acid cycle, running everything through the citric acid cycle, we have created CO2s. Now, when we start a hydrocarbon and we burn it, or we oxidize it, we are going to make CO2. What we haven't done is made water yet. That's the other product. And so oxidative phosphorylation will be the completion of that. We have no more carbons to oxidize, but we have to get everything else. The other item that we made was FADH2 in the citric acid cycle, which is going to give us some energy in terms of the ATP molecule. Again, we created 2 GTPs in the citric acid cycle, but we always count them as ATP because they can be interconverted without loss of energy. What I do want you to understand is the different compartments where everything is made, because it's important. So we made some ATP in the cytosol with glycolysis. We made some GTP, which is ATP, inside the mitochondria through the citric acid cycle. We made some electron carriers in the cytosol. We made some electron carriers in the mitochondria. Knowing how many for the basis of glucose is important because we may have to transfer some of those, and we'll see that in just a moment. The last part is getting those electron carriers to oxygen. Now, if we could transfer the 2 pairs of electrons directly to oxygen and throw a couple protons in there, we create water. And we would extract an extremely large amount of energy. But we can't do that. We actually have to allow the electrons to flow through multiple carriers until we get to oxygen. Now, this loses the efficiency of the energy that is available, because for every movement of electron center, every pair of electrons that move from center to center, whatever it's going to be carried by, it has to go down the energy curve. And so for every jump, I lose a little bit of energy until eventually I get to oxygen. Now, oxidative phosphorylation in an aerobic process can create the largest amount of ATP, and we're going to get 26 out of either the 32 or /30 molecules of ATP that are formed by oxidative phosphorylation. I will tell you why we either have 30 or 32 later in this chapter, and it's important to know. One other thing, in your notes, I combined a couple notes into one slide for the next time I print this, so there's less pages. So all the information you have, it's just ordered just a tad differently. I changed the order this morning. So the mitochondria is where we're looking at, carried out by what we call the respiratory assemblies. They really are proteins that are embedded in the membrane, and these are in the inner membrane of the mitochondria. And what we're going to do is we're going to control the flow of both ions and polar molecules amongst these membranes so that we can create one more energy pool and use it to power the synthesis of ATP. The citric acid cycle, the majority of it, fatty acid oxidation, also occurs in the mitochondria. So we've looked at citric acid cycle. We have not looked at fatty acid oxidation at this moment in time. Also, the pyruvate dehydrogenase complex is inside the mitochondria. So that's the one stage between citric acid cycle and glycolysis. The mitochondria has an outer membrane. It has a lot of permeability due to the presence of a protein called porin. It has a very large hole, thus ions can flow inside and out. Also, small molecules can flow inside and outside that very large pore. And so we've got the inner membrane, the outer membrane. There's an inner membrane space, but there's a lot of exchange to the cytosol because of these proteins. There are two faces of the membrane, referred to as the matrix side, the inside, and the cytosolic side. We can also call it the inner membrane space. We also can call them the inside and the P side. Negative on the inside the matrix and positive on the cytosolic face. So there's an electrical charge difference between the inner membrane and the matrix itself. This is where the next energy pool is going to be created. Remember, we're changing where the energy lies from glucose in the potential. We now have, at this moment in time, some ATP, some electron carriers. And then we're going to change it into what's going to be a proton gradient, a differential in protons across that membrane. So the flow of electrons will go through lots and lots of proteins, all right, that are embedded in the membrane. As the electrons flow through those proteins, what actually occurs is that the protons from the inside of the matrix get pumped out to the inner membrane space. And so you have a large differential, but any gradient is a source of energy. Most of the time when we created a gradient like the sodium gradient and the potassium gradient for a nerve signal, we used the enzyme sodium potassium ATPase. We broke ATP to move them against the gradient to create a very large differential so that we can open up channels and depolarize the cell. Here we're creating a proton gradient. The proton gradient then is coupled to another protein, which is an ATP synthase. The ATP synthase will allow protons to flow through the channel, through the synthase itself. It's not a channel. And it will take the reactants ADP and PI and create ATP. And so that is where we are using the energy of the proton gradient, is to create ATP there. And we create ATP inside the mitochondria. Now, the ATPase, or the ATP synthase, was first discovered as a proton pump. Okay, when we isolated that particular protein and we tried to manipulate it, we gave it some ATP and it pumped out protons. Well, remember, an enzyme stabilizes a transition state. The breaking of ATP transition state is the same transition state as the making of ATP from the two substrates. After looking at that particular protein, we understood that the power of that gradient was going to cause what we would assume would be the reverse. And so some books classify this as a proton pump, but it is the ATP synthase itself. Going back to electrochemistry, bring your calculators to the exam. We can calculate the potential energy, or the delta G, from the negative number of electrons times Faraday's constant times the delta change in potential energy. And if I give you this particular problem, I will give you Faraday's constant. An example, again, these are simple ones that are given inside the textbook. Fumarate plus 2 electrons plus yields succinate. The 2H plus 2 electrons we have written as a hydride, and we've got a energy potential for that. And then the accepting of the 2 electrons as a hydride to make NADH, there is an electron potential for that. And you take the 2 and you look at the overall reaction. And so by the delta E, you can calculate very easily that this particular transformation would not be spontaneous. Another example, would be this. If by chance I took NADH and I donated the electrons to oxygen directly, that's a huge change in voltage, and you would have potentially minus 52.6 kilocalories per mole. Now that's a huge number. Let me show you how huge it is. In terms of ATP, if I convert that energy, we learned it as 30.5 kilojoules per mole. If we put it in terms of kilocalories, it takes 7.3 kilocalories to make ATP. And if you do the simple math, you could synthesize 7 ATP potentially with the transfer of 1 NADH directly to oxygen. Unfortunately, we know that is not the case because we can only make an equivalent of 2.5 ATPs for every NADH that is that we allow the electrons to flow through oxygen. So we use up a very large fraction of the energy just to get it to oxygen, the potential that is there. Now, we're going to flow electrons through a whole bunch of proteins, and we're going to have complex, what we're going to call complex 1, 2, 3, and 4. I show in this case 1, 3, and 4. But what I also want to tell you about is there are other players that carry electrons. We represent another player called Q, and it carries an electrons, and we go back. This is the reduced form. QH2 is the reduced form. Q is the oxidized form in its abbreviation. FMN is an organic molecule that will be embedded in some of these proteins that accept electrons. A protein called cytochrome C is a player. And then basic metal centers can actually accept electrons, and they will be in this pathway. So let's look at the players before we actually look at the process. Q is called ubiquinone. You may also see it as Q10. If you actually watch commercials for, makeup or creams for your face and things like that, I have 3 girls. One of the components that can be in these repair face makeup or face what would I call it, creams, they'll say it has Q10 in it. It's a cofactor. It's organic. It's natural. What it is a very organic molecule that can carry electrons. And what they're doing is they are equating the fact that this Q, who carries electrons in an electron chain, could potentially react with radicals, oxidative species that could damage your skin. And so they isolate this and they put it in, and it's, scientific. And that makes it more expensive because they can put this in here. But for us, this ring system has a very large hydrophobic tail, and that 10 is that repeating unit. That long tail allows this to be soluble in the membrane between the polar regions. So you have a polar region, you have a polar region, and remember you have all those hydrophobic tails. Q is dissolved inside between the polar heads that are interacting with the water, and it moves inside the membrane, back and forth. So it's going to travel inside all of those hydrophobics. Now, it's kind of interesting because if you take a look at this, that is still hydrophobic. Okay? A ketone is a relatively hydrophobic molecule. But when you accept the electrons, we convert that into alcohols. Those are polar. But because of this very large tail, we're still hydrophobic enough to be dissolved in there. You will accept 2 electrons and carry it as 2. You can accept one electron and have a radical, but most of the time what we're going to have is two electrons are going to be carried in the Q. The next FMN is the organic molecule that is part of the FAD. And again, it will hold electrons similarly to the FAD. It can hold a single electron, but it normally holds 2 electrons. Heme is an electron carrier. It carries the electron by donating it right here to the iron. And it will change oxidation states from +2, the reduced, to +3, the oxidized. When was the last time we saw heme? What protein? Hemoglobin, yeah. And hemoglobin is where oxygen bound, and oxygen bound right at that iron. And the iron had a histidine in front and a histidine in back of it, and one of the histidines were connected and one of the histidines was in the way, and oxygen can only bind in an angle. The whole point of the protein in hemoglobin is to make sure that the oxygen doesn't bind directly in, because if oxygen binds directly into the heme, it'll never come off because it binds very, very tightly. So it has to be in the way. The second thing was this. The hemoglobin was there to prevent the oxidation of the iron, because in the +3 state, iron can't bind to or oxygen can't bind to the iron in heme. In cytochrome C, the protein that it's being held, the whole protein is designed so that that iron goes through that oxidation state, and it can pick up one and then donate it later. So even though we're using the same organic molecule, we use it in two different ways within hemoglobin and the cytochrome C, which we'll see. And so this is an electron carrier. Important about this one, it can only carry 1 electron. That's going to create a problem for us, because everything else up to this point carries 2. And so we're going to have issues. Metal centers, there are 2. Coppers we find, and coppers sit inside the protein, and they can go between a +1 state and a +2 state. And so I can carry a single electron there. A lot of times they are in pairs, so that when electrons are donated into the center, one of them is carried in one of the coppers, the other is carried in the other copper. And then we have iron clusters. We have the 2 iron, 2 sulfur, and it has a certain geometry, or the 4 iron, 4 sulfur, and it has a certain geometry. These can carry from 1 to 4 electrons, depending upon which enzyme or which protein you're looking at, but most of the time in our process it's going to carry the 2. So these are places that electrons can be carried. The goal of oxidative phosphorylation, 2 separate processes that are distinct. Pump out the protons and create water to make sure that the electrons go to oxygen. The second, which is separate and distinct but in the same membrane system, is the synthesis of ATP by allowing that proton gradient to flow back into the matrix. Now, when we started looking for what was going on with the mitochondria as good, well, this is way back when there was no biochemist. It was really organic chemists that were dealing with biological systems. They started doing separations. And when they did, they separated 5 functional fractions that were in the membrane that did 5 separate things. One of those was to, now we know it's ATP breakdown, but when they first found it, it would actually, we now know it's synthesis. When they first identified it, it was ATP breakdown. And so at this point in time, when they first isolated, they didn't know what was going on, and they thought it was a pump. We found 4 other fractions that would begin with an electron carrier, and it would transfer electrons to another carrier. And so we named them complex 1, 2, 3, and 4 because we found them. And then that 5th. And then we decided, we did a lot more study once we isolated each one to find out what was going on. The 4 complexes, a lot of times people refer to them as complex 1, 2, 3, and 4 because the names that you see, and I give you the names that are in this textbook, are slightly different in every single textbook you read, and they're different in every journal article that you read, depending upon how far back you go. Unfortunately, they do change their names over time, and so it is sometimes harder to follow that back than what you might think. And so the key to this, complex 1, complex 3, and complex 4 are the only ones that pump out protons. This will be directly in relation to how many ATPs we can make. Complex 2 will accept electrons. It will get it into the chain, but it will not pump out protons, so it won't directly lead to ATP synthesis in the first step, but in subsequent steps, I can. So if I look at NADH, the complexes that it will work with, it will put electrons into complex 1. Inside a box is inside a membrane. Complex 1 will give its electrons to Q to become QH2. If I have FADH2, then I will enter in through complex 2, which will also give it to Qs and carry it as QH2. The QH2 then, at that moment in time, doesn't matter where it came from, will interact with complex 3. Complex 3 will then interact with the protein cytochrome C. And here is a big key. Goes from electrons flowing inside the membranes to a cytochrome C that is floating inside the matrix in water. All right? And then the cytochrome C will float over to complex 4, which is inside a membrane. And molecular oxygen will be bound. The electrons will be accepted by the oxygen, and we will produce water. And so the last would be water produced. Through all this, proton gradient is created. So that is the overview. Here it is, and here's how it looks in terms of the different complexes. The NADH is very direct. Protons flow through. You see Q floating inside the membrane, and it will build up in high concentration, and there is a docking pocket in complex 3 for QH2 to bind. I will eventually give electrons to cytochrome C, which is actually in the intermembrane space. And then cytochrome C will give its electrons to complex 4, producing water. Along the way, protons are pumped, protons are pumped, protons are pumped. Down in the FAD realm, it's a little bit more complex because there's all sorts of places in which the FAD can come from. Now, we call complex 2 here, okay, right there. But after further study, what we find about complex 2 is this. It is the same enzyme of the citric acid cycle that converts succinate to fumarate. The one place that we make FADH2 is in citric acid cycle is complex 2. So if you look at that protein, it can be named either just the succinate dehydrogenase, if you're kind of referencing it from citric acid cycle, or if you're referencing it from oxidative phosphorylation, we call it complex 2, same exact protein. Okay. Now, there are 2 other places in which FADH2 can come in. One is when I degrade fat. Now, we haven't got there yet, and we're going to get there, but there's FADH2 that is synthesized in the degradation of fat, and it has its own protein that will deliver it to QH2. So it still gets to QH2, and it still pumps no protons out. Then there is one protein that we're going to come back to and we'll talk about at near the end of the chapter. It's glycerol 3-phosphate dehydrogenase. It's going to take glycerol 3-phosphate and create dihydroxyacetone phosphate. Now, you know what dihydroxyacetone phosphate is. What path are you in if you have that particular molecule? Glycolysis at this moment in time. Glycerol 3-phosphate is not a glycotic intermediate, okay? But what we are going to see is the electron carrier that is created inside the cytosol from glycolysis has to get inside the matrix. One of the two pathways puts the electron pair into an FAD from an NAD plus and put it into QH2. This is one alternative of how those electron pairs from glycolysis get into the citric acid cycle. All right, it flows through complex 3 and 4 subsequently, just like up here. And I got a proton gradient, and I get a proton gradient, and I can create ATP here. Now, I've got lots of protons up here for one NAD, and I said I could make 2.5 ATP. So that number of protons make 2.5. Whenever FAD enters in oxidative phosphorylation, it can make a total of 1.5 ATP. Even though they're both pairs of electrons, the way that they flow result in two different amounts of ATP potentially. Looking at the complexes, unfortunately, crystal structures of proteins that are embedded in membranes are very hard to make. Crystal structures of proteins are something that are fundamental to our understanding of what biochemistry does. Why would a soluble piece, which is what we see here, this is the piece that is right mimicked here. This is soluble in water, and here's the part of the membrane, or this is the part of the protein that is in membrane. Why in the world could we get a crystal structure of this and not a crystal structure of that? The other part, what? It's in the membrane. But why does that have any effect to getting a crystal structure? I said it was difficult. Why would you predict that the membrane portion wouldn't want to, or is harder to get information from a crystal structure than the soluble part?
Is the membrane hydrophobic?
The membrane is hydrophobic. Remember what a crystal structure is, okay? What you have to do is you have to create conditions in which the protein will form a lattice just like ions form a lattice. Now, if you have a piece of protein that is soluble, at least it's polar on the outside, and it has potential of lining up next to each other and creating a three-dimensional lattice or crystal structure. The hydrophobic, on the other hand, doesn't like to be in water, doesn't like to be in crystal structures. What it does is it likes just to come together and aggregate in a non-uniformed way. Slap all the hydrophobics together and I'm happy. I don't have to order up in a particular crystal-like structure. It's just hard to get a membrane-bound piece of a protein or a membrane-bound protein itself to crystallize because it doesn't like to behave like an ion. It likes to behave like an organic molecule. Now, looking at the crystal structure of this particular protein, there's a key to this. You can see it just a little bit here, and they articulate it very well here. There is a pocket in which NADH sits. It will then donate its electrons to an FMN. That's the organic species that looks like the FAD carrier. Then there's right next to it an iron center, and right next to it an iron center, and right next to it an iron center. They are very close in proximity, such that the electron can jump from one center to the next. What people have termed this is there seems to be a little wire inside the protein in which the electrons are just flowing up that particular path. Now we lose it here because we don't have the crystal structure up here. But we would assume that there continues to be places that are very close in proximity in which the electron can jump, 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 jump. And it can move it physically a very long distance. Now, here's where we lose some of the energy. Every jump, a little bit of energy is lost. It will jump up here until it gets to, and on the surface of this particular protein, the Q that has no electrons can bind to a pocket. Okay, so this is mobile. It looks like it's embedded, but this one is mobile, meaning that it can bind to the protein and then move back into the membrane. And it will sit there until it takes the 2 electrons and it picks up 2 protons, and then it can be mobile and move on. All right. Last step, it says transfers it to QH2, good, and QH2 will increase in concentration inside the membrane until it gets high enough to effectively bind into the pocket in complex 3. The passage of 2 electrons through this complex leads to 4, that's important, protons that are pumped into the inner membrane space. We're going to look at stoichiometry for this. Okay, remember complex 2 has lots of different ways it can go in. All right, we are first looking at it from this perspective. In a, that was complex 1. All right, so we just covered in the last slides complex 1. So this was all last slide. What we're now looking at is this one right here. It goes into complex 2. There are iron centers, and it goes to Q to make QH2. This is the path, but remember, this is also the enzyme that is the enzyme in citric acid cycle. This is what we consider from glucose, how the electrons are getting in the form of FADH2. The other 2, this going through glycerol 3-phosphate to dihydroxyacetone is entry of electrons through glycolysis from the NADH from the glycolysis. And then this whole chain right here is what we will see in terms of breaking down fats. As we break down fats, we will send electrons to FADH2, which then will go into Q. So it's a little bit more complex, but we can enter in the FADH2 from the citric acid cycle. We can enter the electrons from glycolysis that are given in the cytosol, and then fats play into this, and we'll come back to that in, I think, 2 chapters from now. At this point in time, we have electrons in the form of QH2 that can go to complex 3. All right, here is the problem. QH2 has 2 electrons. It is going to take the 2 electrons and give one to cytochrome C. But then it's got an extra electron. What does it do with this? And so the complex 3 has a cyclic process that will regenerate a QH2. So what's going to happen is, overall, I am going to bring two QH2s to the party. Okay? I'm going to give it to complex 3. I will create 2 cytochrome Cs to go on to complex 4. That's cool. Plus, I will make 1 QH2 regenerated. 4 electrons, 2 electrons, 1 in each, and 2 electrons. So 4 electrons come in, 2 get booted to the next step, and 1 comes back that can be go back through. And so it's like kind of driving through a traffic circle instead of coming to a 4-way stop. All right? Some people can just get caught in the traffic circle and never get out. And that's what it kind of looks like. But it gets a little bit complex. Now, if you know how to use a traffic circle, it's actually pretty efficient, but Americans don't know how to use traffic circles. We do have a good crystal structure of this that has helped us understand what the entire process is. Again, there are a lot of places in which the electrons can be accepted. Inside this particular protein, there are 2 hemes, heme groups that can accept electrons, the heme site low and the heme site high. And so we've got some embedded ones. It's kind of interesting because the cytochrome C is going to accept the electrons inside of a heme. There's also the mobile cytochrome C, the one that floats in and out, that docks. And we have a heme C1 or cytochrome C1 that is bound and part of the protein complex that is not mobile. It's complexed. And it's just one stepping stone before it gives it to the mobile cytochrome C. So there's lots of pieces here. All right. Other than crying, what can we extract from this slide? Okay. It looks complex because it's really hard to put this on a two-dimensional piece of paper. So watch. The first QH2 comes in, okay, and it docks to the protein. One of its electrons, okay, will transfer to an iron center. It'll transfer to the cytochrome C1, which is part of the complex and doesn't leave. And it will give its electron to a mobile cytochrome C, which comes in and then goes out, depending upon whether it has an electron or not. I've sent 1 electron on. At the same time, one of the electrons jumps to the heme B site, then the heme H site, and then what happens is a Q that has no electrons binds to the protein, and it will accept 1 electron. Now here's the problem. This never moves. Now I have an arrow that says Q with an ion and a negative charge. What happens is this becomes that sitting here. It just kind of holds on to that 1 electron. The Q that holds on to 1 electron cannot undock from the protein. It just sits there, bound to the protein. All right? The problem is I can't show this in one spot. That's why it has that arrow. So this is an anomaly. That's why it has that little arrow that goes back, says it never actually moved. All right. The original Q that came in with its 2 electrons falls off and is now up in the pool of all the QH2s. That is round 1. Round 2. Another QH2 comes in. It binds to the site. Again, the electrons go up to cytochrome C. That's great. And again, the cytochrome B low, B high, and now it will bind to the Q that has 1 electron, now has 2. It now picks up 2 protons, and this now can float away to come back and be this one or to come back and be that one. Okay? As this process occurs, for the 2 electrons to flow through, we get protons pumped from one side of the membrane to the other. That's important. But there's also another part of the gradient that is created. Remember, a gradient means the concentration of H has to be high, and the concentration of protons here has to be low. If I actually take protons and move them through from one side to the other, I make one high, one low, right? That seems reasonable. But this process right here, where protons are taken from the inside and combined to QH2 here, also makes that lower without pumping anything across. So there's more energy created than just putting it across. I actually put it across to make this one higher, and I suck up extra protons inside the matrix to make it lower. All right. So, as you have all of this, the electrons flowing through, the stoichiometry has 4 that are chasing it around. The complex number 4, all right, stoichiometry is a little bit different at this moment in time because we just had 2 electrons go through and we had one cytochrome C and another cytochrome C. We got 2 cytochrome Cs. If you follow the stoichiometry all the way out, you would only make a half of oxygen. And we don't actually make a half of oxygen. So what we're going to do is we're going to double it at this moment in time so that we can create 1 oxygen molecule. So the stoichiometry changes a bit. What we're going to do here is we're going to have iron centers and copper centers. And 4 electrons will come in one at a time. And we're going to have eventually 4 protons pumped from one side to the other. In this, oxygen will be bound between reactive metal centers, such that the electrons will first be accepted by the metal centers, and then the oxygen will accept them. And they are accepted one at a time. So, of all of that complex, there is a really special pair of iron and copper that are reactive. The copper, before any electrons come into this, is in a +3 state, and the copper's in a +2 state. 1 electron will come in and reduce the copper to a +1. A second electron will come in and reduce the iron to a +2 state. This allows oxygen to bind. Oxygen is excluded here because the coordinations can't allow oxygen to get inside. There's no place for the lone pairs of oxygens to coordinate. Here, I do have a way in which the oxygens can bind, and you can see oxygen gets in the mix and it binds at an angle to that iron, just like hemoglobin, to make the oxygen-iron bond weaker. Now, got lots of extra, I have an extra electron here and an extra electron there. Throws an electron in, throws an electron in. Oxygens are very electronegative, and so now I have an extra electron and an extra electron. So oxygen with a double bond and 2 negative charges. That doesn't look happy. Not at all. But we have a lot of positive charge that is coordinating. And so they're not just sitting there, but those extra pairs of electrons are still coordinating to the metal centers. All right, now it gets really freaky. I throw in 1 more electron, okay, and a couple protons. What happens is we break the double bond. One of the oxygen picks up 2 of the protons, and there's a bond here. Remember, when you coordinate 2 metal centers, these lone pairs can, and that probably should be formally a dotted line rather than a full bond, and it's coordinating. Then you get this strange thing. Iron 4+ double bonded to an oxygen that has a 2-. Again, not a really stable intermediate. Doesn't stay around too long. You throw 1 more electron in that mix and 2 protons, and the second water will form. Both waters fall off, and we we oxidize the 2 metal centers back up to the iron 3 and the copper 2 state. And so, really strange electrochemistry that happens here. This is really facilitated by the metal centers in this complex, and we can produce water, and we have used 1 oxygen in that whole process. All right, here's the stoichiometry. For NADH, complex 1 pumps out 4, complex 3 pumps out 4, and complex 4 will pump out 2 because the stoichiometry, remember I showed you 4, but for 1 NADH, it would be only 2 electrons. So I get a total of 10. For FADH2, complex 1 doesn't pump anything out, complex 3 pumps out 4, complex 4 pumps out 2, and so I either pump out 10 protons or I pump out 6 protons. This is where the pool of the energy has totally converted for almost all of the carbons in glucose. All right, we'll come back to these stoichiometries. The ATP synthase actually has a very similar structure to some of the other proton pumps, and again, it is there to stabilize the transition state for the ADP and the PI to come together. What is really important is the different pieces of the puzzle. All right, you've got 6 proteins called the AB dimers. That is where the ADP and PI are going to bind and actually come together. Okay, you've got a chamber that the protons will flow through from one space to the next. You have a embedded alpha helix still embedded in the membrane itself. And then you have 3 proteins, gamma, epsilon, and delta. Each of these 3 proteins are differently shaped. And what really happens is the gamma interacts with 2 of the pair, an alpha-beta pair. The delta will interact with an alpha-beta pair. And the epsilon will interact with an alpha-beta pair. Depending upon which one it does, which one it interacts with, the alpha-beta pairs will be in 3 different conformational states. So an alpha-beta pair touching gamma looks different, or touching epsilon looks different, or touching delta looks different. Okay, and that's the interaction. What's going to happen is, as the protons come through, we're going to spin some of this. And the alpha-beta pairs will once be associated with one of those 3 proteins, the delta, the epsilon, or the gamma, and then it'll rotate and interact with the next one, and it'll rotate, and what happens is it goes from one conformational state to a second conformational state to a third conformational state and back to its original as protons go, and so we get this spinning. The F0 unit is where the protons actually flow through. It can be affected by oligomycin, and so that's an FO, not an F0, because oligomycin blocks the channel. Oligomycin is an antibiotic, and it can kill an organism. And obviously, if you stop ATP production, it'll eventually die. The F1 segment, when you isolate it by itself, just that portion, it works as an ATPase. It will break down ATP, and for a long time that kind of led researchers in the wrong direction. Here is the synthesis of ATP. Mechanistically, we've seen very similar reactions in glycolysis. I attack here, and I tell you, I kick up, and then I say kick down. But here's the kick up. This is what is actually happening. You get a pentacovalent intermediate along this phosphorus. Sorry, I drew my arrows wrong. It's going to attack, sorry, this way. There, and kick up, because I'm putting them together. All right, GChem question time. What is the hybridization of that phosphate? My GChem 1 students can answer that question. Okay, my Biochem 2 students answer that question. It's one of those things you learn and like, I knew it for the test, right? How many things are bound to that phosphorus? 5, right? So, you have to mix how many orbitals to create 5 bonding pairs? You have to mix the S, right? And all 3 P's, right? And 1D. It is sp3d hybridized. What is the electron pair geometry around that phosphorus? If there are 2 pairs, it's linear. If it's 3 pairs, it's trigonal planar. If it is 4 pairs, it's tetrahedral. And since you've been in organic chemistry, that's all you know, right? What's past that? If it's 5 pairs, it's not square pyramidal. Good guess. You're heading in the right direction. That's an octahedral with 2 lone pairs. Yeah, trigonal bipyramidal or trigonal bipyramidal, where you have a little pyramid, triangle pyramid on the top and triangle pyramid on the bottom. Oh my goodness, it all connects. All right, that's a high energy state. And you can see why that is a high energy state. Not only does ATP not, have a lot of charge, we have now put a whole bunch of charge right there on that phosphorus. And so that's what has to be stabilized. Now to finish the reaction, we kick down and we kick off, and what I normally say is something like it picks up a proton. All right, and so I usually say kick up, kick down. This is the first time I've articulated when you attack that. That is a pentacovalent 5 bonds in the intermediate, and then we'll get ATP at the end. All right. If we take a look at the crystal structure of the alpha beta pairs. Okay, here's the good thing about crystal structures and the really, really bad thing about crystal structures. To a crystallographer, they can see, I don't know, magically, that those 2 pairs, that each one of those pairs is slightly different. When I look at them, they look like blobs, right? That's why they make this picture, and you can see the kind of the squarish drawings here. It's shaped differently. This one's shaped differently, and that one's shaped differently. All right. In this case, there is no ADP or PI bound in this particular shape. Here, they crystallized it with the ADP sitting here. And here, they crystallized this, and the shape has ATP in the active sites. And so I have 3 different shapes, and they have different affinities to different things to bind. This has a very low affinity for either ADP or ATP. This is called the open form. Here, ADP and PI actually bind. They didn't trap PI because in the experiment they didn't put PI inside of it because they wanted to stall the reaction to try to create a crystal. This is called the loose site. In this site, ATP was there. This is called the tense site or the tight site. Okay? And so one of those three inner proteins, when it interacts with these two pairs, creates the open. One of those creates the loose, and one of those creates the tight. And so what can happen is, in the loose, the two substrates fall in. In the open, ATP was in there and it falls off. Okay? And so as protons flow, the inner site moves and it will change this one, the L, and make it look like the tight. This one, when it rotates, will become the open, and this one will become the loose. When this becomes open, ATP falls off. When this becomes tight, those two come together, and when this becomes loose, it will pick up the next pair of reactants. Now, an experiment is done at the bottom, and what they did was they put an actin filament and they attached it to the FO portion of the ATPase, and they linked the AB portions to a slide. And what they did was they gave it some ATP, and ATP started breaking down. Okay? And what they showed was, okay, this is what they showed. As the experiment went on, do you see the orientation for these? They're oriented this way. Then all of a sudden, they orient and they change orientation, and now they're in this way. That change is about 120 degrees. And then over time, and now it's there for a while, over time you see it transition into a third state, which is another swing of about 120 degrees. And it stays in that site until it swings back and goes to the original position. And so there are three different states that twist around for those three pairs. And this helped identify that three-pronged transition. All right. Let's take a look at a video about what this would look like as it's actually happening.